Light bends where space itself is curved. Across the universe, immense gravitational fields twist the fabric of reality into cosmic labyrinths, invisible mazes where photons can become forever lost. This is not science fiction, but the direct prediction of Einstein's theory of general relativity. By the end of this journey, you will understand how these distortions of spacetime fundamentally alter our perception of the cosmos. We will explore why some light escapes to tell its story while other rays vanish into eternal darkness, and we will decipher the true meaning behind a black hole's shadow. Are you ready to see the universe not as a void, but as a living, breathing geometry? Think of a bowling ball resting in the center of that trampoline. It creates a deep, smooth well, and a marble rolled nearby will naturally curve inward, tracing a path around the depression. This is the essence of gravity, not as a mysterious force reaching out across space, but as the natural motion of an object following the contours of a curved landscape. The sun warps the spacetime around it in exactly this manner. A photon of light traveling from a distant star and skimming past the sun does not travel in a perfectly straight line. Instead, it follows the curve of this spacetime depression, its path bending ever so slightly. This was one of the first and most dramatic confirmations of Einstein's theory, observed during a solar eclipse when stars appeared slightly out of place because their light had been curved by the sun's gravity. But what happens when the bowling ball is replaced by something unimaginably denser? The gentle slope of the trampoline transforms into a deep, shear-sided funnel. This is where the geometry of space becomes a labyrinth for light itself. The curvature becomes so extreme that the possible paths anything can take, including light, are twisted into a complex maze from which there is no easy exit. This is the transition from simple bending to a cosmic trap, a region where the fabric of space is folded over upon itself. For centuries, the path of a light beam was the very definition of straight. It was an unbreakable rule of the cosmos, a line drawn by geometry itself. Then came Einstein, who revealed a profound truth. Light does not bend. It remains utterly faithful, always following the straightest possible path through the universe. The shocking part is that the universe itself is curved. That straightest path, what physicists call a geodesic, is rarely the straight line we imagine. It is the natural, shortest route across a landscape that has been warped and folded by mass and energy. This is the heart of gravitational lensing, a cosmic illusion where the very fabric of reality acts as a lens. A massive galaxy cluster, for instance, does not pull at light with some invisible force. Instead, it creates a vast dimple in spacetime, and the light from objects behind it simply follows the contour of that dimple on its way to us. The result is that we might see multiple stretched and distorted images of a single, distant galaxy, its light having taken several different routes around the cosmic obstacle. The strength of this lensing effect is a direct consequence of the mass involved and the intimacy of the encounter. A gentle curve far from a star becomes a tight, spiraling whirlpool near a black hole. Here, the curvature is so severe that light can be forced into stable orbits, circling the abyss multiple times before it finally manages to break free on a new trajectory, or fails entirely and is drawn inward. This path alteration fundamentally changes our perception. The sky we see is not a flat map, but a dynamic, three-dimensional tapestry where gravity has rearranged the light, creating mirages and echoes of cosmic events. To grasp how this gentle bending escalates into an inescapable maze, we must venture to the place where these curved paths finally close in on themselves. The marble rolls smoothly into the bowl, a simple and familiar motion. But if the bowl's sides grow impossibly steep, that smooth curve transforms into a trap. The marble crosses a point of no return, unable to climb back out, destined to spiral inward. This is the precise moment when the curvature of spacetime ceases to be a gentle guide and becomes a perfect prison for light. Around the most ultra-dense objects in the cosmos, the fabric of reality warps into a gravitational well of such profound depth that nothing, not even light itself, can escape once it crosses a critical boundary. This boundary is known as the event horizon. It is not a physical surface you could touch, but a mathematical point of no return, a one-way door in the geometry of the universe. The common explanation is that the escape velocity here exceeds the speed of light, but this is a simplification. The reality is far stranger. It is not that light is being pulled back by a force. Instead, the curvature of spacetime itself becomes so infinitely steep that all possible paths for any particle or photon, every direction it could possibly travel, point inexorably inward toward the central singularity. For a simple, non-rotating black hole, the size of this spherical trap is defined by the Schwarzschild radius. Within this region, the very idea of an outward path ceases to exist. The geometry of the cosmos folds over completely, creating the ultimate cosmic labyrinth. Light enters this maze and finds every corridor, every potential route, leading only deeper into the abyss. It does not slow down or struggle. It simply follows the straightest possible path through a universe that has been curved into a closed loop from which there is no exit, vanishing entirely from our observable reality. To truly comprehend how such a bizarre and absolute prediction emerges not from fantasy but from rigorous logic, we must turn to the mathematical framework that first mapped this terrifying geometry. The beauty of Einstein's field equations lies in their elegant, almost poetic simplicity of concept, yet their profound complexity in execution. These 10 interconnected formulas are the universe's own blueprint, dictating how the presence of matter and energy commands the fabric of spacetime to curve. The equation g mu nu equals 8 pi g over c to the 4th times t mu nu is the heart of it all. On one side, you have g mu nu, which describes the geometry of spacetime, its curvature and warp. On the other, t mu nu, which represents the energy and momentum of everything within that space, from stars to radiation. The equal sign in the middle is the revolutionary link, declaring that mass tells spacetime how to curve, and that curved spacetime tells mass how to move. This relationship is not a gentle suggestion, but a dynamic, point-by-point negotiation happening everywhere, all at once. The curvature is not a single, smooth bowl. It is a complex, ever-changing landscape of hills and valleys, dimples and funnels, each shaped by the local concentration of mass and energy. Solving these equations is one of the greatest challenges in physics. We can find exact solutions only for idealized, perfectly symmetrical situations. Karl Schwarzschild found the first such solution while serving on the Russian front during World War I, describing the spacetime around a single, non-rotating spherical mass. His solution directly predicts the existence of the event horizon, that point of no return. For a rotating black hole, the solution found by Roy Kerr is even more fascinating, revealing a spacetime that is not just curved but dragged into a swirling vortex around the spinning object. But the real cosmos is messy, filled with colliding black holes and swirling galaxies. For these chaotic events, we turn to numerical relativity, where supercomputers break spacetime into billions of points and calculate how the curvature evolves from one moment to the next. It is through this monumental computational effort that we can simulate the ripples in spacetime we call gravitational waves. watching as the labyrinthine geometry of the universe shifts and rearranges itself in real time. This mathematical foundation moves us from pure theory to tangible prediction, allowing us to map the invisible architecture of the cosmos. So what happens when we point our telescopes toward the sky, searching for the shadows cast by these ultimate cosmic labyrinths? These mathematical predictions find their most stunning confirmation in a cosmic illusion known as gravitational lensing, nature's own magnifying glass. When the light from a brilliantly luminous but incredibly distant galaxy travels across the universe, its path can be intercepted by the immense gravitational field of a massive galaxy cluster in the foreground. The cluster does not capture the light. Instead, it sculpts the space around it into a vast, transparent lens, bending the incoming rays of starlight as they pass through this warped region. The result is not a single, clear image of the background galaxy, but a celestial mirage. We might see multiple, shimmering copies of the same galaxy arrayed in a perfect circle, a shimmering halo of reconstructed light known as an Einstein ring. Other times, the light is stretched and smeared into long, luminous arcs, like great celestial rainbows painted across the blackness of space. This phenomenon reveals itself in three distinct forms, each a testament to the strength of the gravitational curvature at work. Strong lensing is the most dramatic, creating those clearly separated multiple images and graceful arcs, a direct visual signature of a profound space-time warp. Weak lensing is far more subtle, causing statistically detectable distortions in the shapes of thousands of background galaxies, a gentle shearing of the cosmos that reveals the presence of otherwise invisible dark matter. Then there is microlensing, a transient brightening that occurs when a single star or planet drifts perfectly in front of a more distant star, its gravity focusing the background starlight like a fleeting magnifying glass and causing it to temporarily flare in our telescopes. For astronomers, these effects are not mere curiosities. They are among the most powerful tools in all of cosmology. By analyzing the patterns of these distorted images, scientists can literally map the distribution of dark matter, the invisible scaffolding that holds galaxies and clusters together. They can peer further back in time than ever before, using these natural telescopes to observe the faint, infant galaxies that formed just after the Big Bang, objects whose light would otherwise be far too weak to ever reach our eyes. The iconic Hubble Deep Field images are filled with these ghostly apparitions, proving that this cosmic lensing is not a rare event but a fundamental part of how we see the universe. Yet sometimes the alignment of masses is so perfect and complex that these simple mirages evolve into something far more intricate. What happens when the curvature of space does not create a single, clear lens, but a hall of mirrors so complex it becomes a true labyrinth for light? Sometimes a single cosmic event can appear in the sky not once but multiple times. This is the magic of multiple imaging, a phenomenon where the curvature of spacetime around a massive object acts less like a simple magnifying glass and more like a complex hall of mirrors. Light from one brilliant quasar or a single exploding star takes not one, but several different routes around an intervening galaxy cluster. Each path navigates a different contour of the warped spacetime, some taking longer journeys than others. The result is a celestial echo chamber. We see the same object repeated around the lens in a precise, intricate pattern, a cosmic signature of the labyrinthine geometry it had to traverse. This means a supernova's brilliant flash might be seen in one image, and then months or even years later, the very same flash will appear in a different image of the same galaxy, a ghostly replay written in light. The theoretical framework that predicts these astonishing patterns revolves around structures known as caustics. Imagine the light from a background galaxy flowing through the warped spacetime like water flowing over a complex, rocky streambed. A caustic is the specific, sharp line where that flowing light is focused most intensely, like sunlight glittering on the bottom of a swimming pool. In the mathematics of lensing, these caustic surfaces are where the mapping from source to image becomes singular, leading to a theoretical spike of infinite brightness. In reality, the finite size of the source star or galaxy prevents a true infinity, but it does create those exceptionally bright and multiple images we observe. The first dramatic confirmation of this came with the twin quasar, known to astronomers as Q0957 plus 561. What appeared to be two identical quasars close together in the sky was in fact a single quasar whose light was being split into two separate paths by the gravitational field of an entire galaxy positioned directly in our line of sight. These multi-path journeys are the beginning of true cosmic labyrinths, where light is guided through a maze of curved space. But when the curvature becomes even more extreme, the paths available to light can twist into closed loops, creating orbits from which escape is nearly impossible. Deep within the gravitational well of a black hole, just outside the point of no return, lies a region of pure optical illusion. This is the Photon Sphere, a place where the fabric of spacetime is curved into a perfect circular track for light itself. Here, photons are forced into unstable orbits, endlessly circling the abyss like marbles rolling around the rim of an impossibly steep bowl. For a simple black hole, this cosmic carousel exists at precisely 1.5 times the radius of the event horizon. A photon arriving at this exact angle with this precise trajectory will neither plunge into the darkness nor fly away into freedom. It enters a state of gravitational purgatory, tracing a circular path around an object it can never truly see. Yet this balance is terrifyingly fragile. The slightest perturbation, a tiny nudge from the gravitational influence of a passing star or even another photon, will upset this delicate dance. The orbiting light is then cast from its circular path, destined for one of two fates. It might be flung outward, finally escaping the black hole's grip to tell a twisted story of its journey. Or it might be tipped inward, vanishing across the event horizon forever. This is not a stable orbit like a planet around a star. It is a knife-edge equilibrium, a transient moment in the life of a photon that reveals the absolute precision of Einstein's geometric universe. The visual consequences of this phenomenon are what allow us to photograph a black hole's shadow. The dark silhouette at the center of images from the Event Horizon Telescope is not the event horizon itself. It is a region roughly 2.5 times larger, a shadow cast because light from the bright material behind the black hole is being bent around it on all sides. The brilliant ring of fire that encircles that darkness is composed of photons that are not in perfect orbits, but are skimming through the Photon Sphere region. Their paths are bent so severely that they loop around the black hole multiple times before managing to escape in our direction. We are essentially seeing light that has orbited the cosmic trap, creating a luminous halo from photons that have navigated the labyrinth's outermost walls. This ring is a direct map of the Photon Sphere, a ghostly imprint of those unstable circular paths where light is neither lost nor free. When multiple ultra-dense objects orbit one another, their individual photon spheres and gravitational fields intertwine. The simple, circular track becomes a chaotic web of curved space. How does light navigate a labyrinth built not by one gravitational master, but by two or more? The dance of two black holes orbiting one another creates a gravitational landscape of almost unimaginable complexity. Their individual wells of curved spacetime do not simply add together. They merge and interact, generating a dynamic, swirling vortex of gravity that shifts with every passing moment. As these cosmic titans spiral around their common center, the labyrinth of curved space they create is constantly being rewritten. A path for light that was open one moment might pinch shut the next, while a new escape route could suddenly emerge. This is not a static maze, but a living, breathing architecture of gravity, where the walls themselves are in motion. Supercomputer simulations of these binary systems reveal a breathtaking phenomenon. The patterns of light and shadow are not smooth or simple. They form intricate, infinitely detailed fractal webs, networks of brilliant caustic lines where light is focused to incredible intensities, right beside regions of utter darkness where background stars are completely erased from view. A single distant galaxy, seen through this chaotic lens, might be fractured into dozens of shimmering, dancing images, each one a ghost tracing a different path through the evolving gravitational storm. The recent detections of gravitational waves from merging black holes by observatories like LIGO provide the perfect real-world anchors for these theoretical models. We now know these systems exist, and their violent spirals must generate these very curvature networks. Light attempting to traverse this space would find itself on a roller coaster ride through a funhouse of gravity, its path twisted and folded by the orbital motion of the masses. This demonstrates that the ultimate cosmic labyrinths are not built by solitary monsters, but by their intricate, entwined dances. So how do we move from these theoretical simulations to actual proof, to catching these gravitational illusions in the very act of warping our view of the cosmos? The Einstein Cross presents one of the most perfect examples of this celestial architecture. In the constellation Pegasus, a single, intensely bright quasar is refracted by the gravity of a foreground galaxy into 4 brilliant points of light, arranged in a near-perfect symmetry around the galactic core. This is not 4 separate objects, but one, its light divided and redirected along 4 separate paths through the curved spacetime surrounding the galaxy. Each image we see is a ghost, a light echo traveling a different length through the cosmic labyrinth to reach us. On an even grander scale, the galaxy cluster Able 370 acts as a far more complex lens. Its immense gravitational field, dominated by the unseen hand of dark matter, warps the light from galaxies far behind it into spectacular, shimmering arcs. One of the most famous of these has been nicknamed the Dragon, a long, luminous shape that upon closer inspection reveals itself to be multiple, duplicated images of the same spiral galaxy, stretched and folded along a critical curve of spacetime. These are not artistic interpretations, they are direct photographs of gravity's influence on reality itself. The value of these mirages extends far beyond their breathtaking beauty. By carefully measuring the positions, brightness, and time delays between these multiple images, astronomers can perform extraordinary cosmic calculations. They can measure vast distances across the universe with unprecedented precision, providing independent checks on the cosmic distance ladder. They can map the invisible distribution of dark matter within the lensing cluster, revealing the hidden skeleton that dictates how visible matter assembles. These natural experiments test the predictions of general relativity under conditions of immense gravitational fields, and so far, Einstein's theory has passed every test. Programs like the Hubble Space Telescope's frontier fields leverage this very principle, using massive clusters as natural telescopes to peer deeper into the cosmos than ever before. By staring at these gravitational lenses, Hubble revealed faint, infant galaxies from the dawn of time, whose light had been amplified and bent by the foreground clusters. These are galaxies we simply could not see otherwise, their light made visible only by its journey through a cosmic maze. Every distorted arc and duplicated image confirms that the universe is filled with these functional, observable labyrinths. They are not rare anomalies but fundamental features of a cosmos where mass sculpts the paths of light, revealing a hidden structure woven into the fabric of space itself. This cosmic web of curvature introduces a profound challenge for modern astronomy. Every distant galaxy we observe, every flash of light from the edge of the observable universe, has traveled for billions of years. During that immense journey, its light has not sailed through empty, flat space. Instead, it has navigated a vast, shifting labyrinth of gravitational potentials, a landscape molded by the invisible cosmic web of dark matter and galaxies. The path of each photon is subtly tweaked and sheared by this large-scale structure, a phenomenon known as cosmic shear. The collective shape of billions of distant galaxies appears ever so slightly distorted, as if viewed through a faint cosmic lens. This is not the dramatic lensing that creates giant arcs or Einstein rings, but a far more subtle, statistical warping of the cosmos itself. It is a whisper of curvature written across the entire sky. Missions like the European Space Agency's Euclid are designed to listen to this whisper. By meticulously measuring the shapes and orientations of billions of galaxies, Euclid's sensitive instruments can detect the minute distortions imprinted by this cosmic shear. This data allows scientists to create a three-dimensional map of the dark matter distribution, charting the invisible filaments and voids that form the backbone of our universe. This grand map of curvature is essential because every time we look at a distant supernova to measure the universe's expansion or study the cosmic microwave background, the light from these events has been slightly altered by its long journey through the cosmic maze. If we do not account for this pervasive lensing, our measurements of fundamental properties like dark energy could be skewed. The universe we see is therefore a carefully reconstructed image, one that requires us to understand the labyrinthine paths its light has traveled. This cosmic shearing of light presents a fundamental problem for observational astronomy. The very curvature that creates these stunning mirages also systematically distorts our view of the cosmos, introducing a layer of complexity to every measurement we make. Consider the simple task of counting galaxies. When a single, distant galaxy is lensed into multiple, distinct images around a foreground cluster, an astronomer's catalog could mistakenly list it as 4 or 5 separate objects. This gravitational illusion can artificially inflate galaxy counts, potentially skewing our understanding of how structures form and evolve across cosmic time. Similarly, the rate of supernova explosions, crucial for measuring the universe's expansion, becomes difficult to pin down. A single stellar explosion might appear to happen multiple times, months or even years apart, as its light arrives via different paths. Without careful modeling, we might count one event as several, misreading the true rhythm of stellar deaths. The challenge deepens when we try to measure cosmic distances. Astronomers rely on standard candles, objects like certain supernovae whose intrinsic brightness is thought to be known. By comparing how bright they appear to us with how bright they truly are, we can calculate their distance. But gravitational lensing throws a wrench into this elegant system. The same supernova, when observed in 2 different lensed images, can appear with drastically different brightnesses. One path through the curved spacetime might focus its light, making it seem anomalously brilliant and therefore artificially close. Another path might defocus the light, making the same object appear dimmer and farther away. An astronomer seeing only one of these images could draw a completely wrong conclusion about the universe's scale. Even the study of cosmic variability is not immune. Quasars, the brilliant cores of active galaxies, flicker and flare over time. When their light is split into multiple images, each flare is seen repeatedly, with a time delay between each apparition. To understand the quasar's true, intrinsic behavior, scientists must first untangle these gravitational echoes from the actual signal. Every observation of a distant object is therefore an inverse problem. We see the final, distorted image, and we must work backwards using our understanding of general relativity to deduce the true properties of the source and the precise structure of the invisible labyrinth its light had to navigate. This requires immense computational power and sophisticated models to map the unseen distribution of dark matter acting as the lens. As we refine these techniques to see through the deception, we must also ask how this pervasive curvature has shaped our view of the universe's deepest history. The oldest light in the universe carries the imprint of every gravitational maze it has ever crossed. This is the cosmic microwave background radiation, a faint afterglow from the Big Bang that has been traveling for over 13 billion years. During its immense journey, this primordial light did not fly through a static, empty space. It traversed a cosmos that was rapidly evolving, its path subtly bent and its energy minutely shifted by the gravitational pull of every growing cluster of dark matter and galaxy it passed. This integrated journey, known as the Rees-Simon effect, leaves a specific fingerprint on the CMB's temperature map. As light climbs out of a deepening gravitational well, it loses a tiny amount of energy, appearing slightly colder. Conversely, light falling into a potential well gains energy, appearing marginally warmer. But because these large-scale structures are evolving as the light passes through, the effect is not perfectly symmetric, creating a unique pattern of hot and cold spots that is a direct record of the universe's growing architectural complexity. We are not just seeing a baby picture of the cosmos, we are seeing that picture as it has been subtly refocused by the gravitational lenses of an adolescent universe. This same principle applies to the most distant galaxies now being revealed by the James Webb Space Telescope. We are observing them during the epoch of reionization, when the first stars and galaxies were lighting up and burning away the cosmic fog. Their light is incredibly faint, and to see them at all, we often rely on the magnifying power of massive foreground galaxy clusters. These clusters act as natural telescopes, bending and amplifying the light from these infant galaxies that would otherwise be invisible. But this gift of magnification comes with a cost, the potential for profound confusion. What appears to be a single, bright, early galaxy might, in fact, be multiple, duplicated images of the same object, its light split by the gravitational lens. Its shape could be stretched into a long, thin arc, distorting our measurements of its true size and structure. Its apparent brightness could be artificially enhanced, making us overestimate its mass and star-forming fury. To understand the true nature of the first galaxies, astronomers must become cosmic detectives, using sophisticated models to reverse engineer the lensing effects, subtracting the distortions of the gravitational maze to reveal the authentic object hidden within. Every observation of the deep past is therefore a carefully reconstructed image, its truth contingent on our understanding of the curved space its light had to navigate. This brings us to the theoretical limits, where the curvature of spacetime is no longer a subtle lens but an absolute mathematical extreme. The mathematical elegance of general relativity holds secrets far stranger than black holes. The same equations that predict the inescapable event horizon also permit the existence of wormholes, theoretical bridges threading through the folded fabric of spacetime. Imagine our universe as a vast, curved sheet of paper. A wormhole would be a tunnel connecting two distant points, a cosmic shortcut bypassing the long journey across the surface. Light or anything else traveling through this tunnel could traverse galactic distances in an instant, navigating a labyrinth that rewrites the very map of the cosmos. Yet this incredible possibility comes with a formidable catch. For such a tunnel to remain open and traversable, it would require a form of matter with negative energy density, something that exerts a kind of repulsive gravity to keep the throat of the wormhole from instantly collapsing. No such exotic matter has ever been observed, and its existence remains one of the greatest speculative puzzles in theoretical physics. Even more mind-bending are the closed time-like curves that appear in certain specific solutions to Einstein's field equations, like the one describing a rotating cosmic string of infinite density. These are not paths through space, but paths through spacetime itself that loop back on their own origin. A photon following such a curve could, in theory, return to the exact event where it was first emitted, arriving before it even left. This creates a direct violation of causality, the fundamental principle that cause must always precede effect. The potential for paradox is immediate and profound. Could such a returning photon interfere with its own creation? The mere possibility suggests that these extreme curvatures, while mathematically consistent, may be physically forbidden by laws of nature we do not yet fully understand, likely involving the quantum structure of spacetime. These theoretical extremes represent the absolute frontier of the cosmic labyrinth, where the geometry described by Einstein becomes so twisted that it challenges the logical foundations of reality itself. They are not just scientific curiosities. By pushing general relativity to its logical limits, physicists discover the precise points where the theory must break down, revealing where the quantum world of probabilities and uncertainties must take over to paint a complete picture of gravity. This is the quest for a theory of quantum gravity, a framework that can describe the labyrinth not as a smooth classical geometry, but as a seething, dynamic quantum foam at the smallest possible scales. The smooth geometry of Einstein's universe begins to fray at its edges when we introduce the bizarre rules of the quantum world. Here, where gravity meets the probabilistic realm of the very small, the cosmic labyrinth gains a new layer of profound complexity. Consider the vacuum of space, which quantum field theory tells us is not truly empty. It is a seething foam of virtual particles, pairs of matter and antimatter that constantly flicker into and out of existence. In the perfectly flat spacetime of a static universe, these pairs annihilate too quickly to be noticed, but place this quantum foam near the event horizon of a black hole, where gravity creates an immense tidal force in the fabric of spacetime, and something extraordinary happens. One particle from a virtual pair can fall across the horizon while its partner is left stranded outside. The abandoned particle, robbed of its partner, can no longer vanish. It becomes real, carrying energy away from the black hole. This is Hawking radiation, a slow, quantum mechanical evaporation where even black holes are not truly black, but glow with a faint heat born from the interplay of curvature and quantum uncertainty. A similar effect, known as the Unra effect, occurs for an observer accelerating rapidly through empty space. From their perspective, the calm vacuum appears as a warm bath of radiation, a direct result of their motion through the quantum fields. This tells us that the very concept of a particle is not absolute, but depends on the motion of the observer and the curvature of the spacetime they inhabit. The light we see is not just following curved paths, it is emerging from the vacuum itself, its very existence shaped by gravity's grip. These quantum effects become dominant in the most violent chapters of cosmic history. In the frenetic first moments after the Big Bang, as spacetime expanded and curvature fluctuated wildly, these quantum tremors were amplified across the entire universe. This process, known as particle creation from the vacuum, flooded the young cosmos with a background sea of real photons and other particles. their birth directly tied to the dynamic curvature of the infant universe. Even today, near an evaporating black hole in its final moments, this rapid change in curvature creates a last bright burst of radiation, a quantum spark from a dying gravitational trap. The study of quantum optics in curved spacetime pushes these ideas even further, asking how fundamental quantum properties like entanglement are affected by gravity. Entanglement is that strange connection where two particles share a single quantum fate, instantly influencing each other no matter how far apart they drift. What happens to this delicate link when the particles traverse different paths through a warped gravitational landscape? Does the curvature of spacetime weaken or even sever this quantum bond? The answer could have profound implications for the future, potentially affecting the design of ultra-secure quantum communication satellites that must transmit entangled photons across vast, curved distances in Earth's orbit. These quantum gravitational phenomena, while subtle, reveal that the cosmic labyrinth is not merely a classical maze of curved space. It is a dynamic quantum entity where light can be born from emptiness, where the definition of a photon depends on your path, and where the most fundamental links in nature are tested by gravity's geometry. This intricate dance between the quantum and the gravitational forces us to confront one of the most perplexing puzzles in modern physics, a paradox that strikes at the heart of what we can ultimately know about the universe. But when a single photon vanishes forever into a black hole, what happens to the story it was telling? This question leads us directly to one of the most vexing puzzles in all of physics, the black hole information paradox. Quantum mechanics, the rulebook for the subatomic world, states with absolute certainty that information is never truly destroyed. Every detail about how a particle was created, its energy, its spin, its very identity, must be preserved in some form forever. It can be scrambled but never erased from the universe, yet classical general relativity presents us with the ultimate shredder. When light crosses the event horizon, it and every bit of data it carries is gone. It is erased from our universe, seemingly violating a fundamental law of quantum physics. For decades, physicists assumed this was not a real problem, that the information was simply hidden, locked away inside the black hole. But then Stephen Hawking made a shocking discovery. He showed that black holes are not completely black, they slowly evaporate by emitting radiation. And this Hawking radiation, according to his original calculations, is purely thermal. It is random noise like the heat from a stove, carrying no information whatsoever about what fell in. So when the black hole finally evaporates completely, all the information about every star, every planet, every photon that ever fell into it would have been permanently lost. This is the paradox in its purest form. How can the universe reconcile these two foundational theories that give completely contradictory answers? Proposed resolutions push the boundaries of our imagination. One compelling idea is the holographic principle. It suggests that all the information about everything within a volume of space is not stored throughout that volume, but is instead encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. For a black hole, this means the information of every infalling particle is not lost inside, but is smeared and stored in tiny, Planck-length pixels on the surface of the event horizon. It is then slowly and chaotically released in the Hawking radiation as the black hole evaporates. Another, more violent proposal is the firewall hypothesis. It argues that instead of a smooth, empty space at the event horizon, there exists a searing wall of high-energy particles. Any object or light beam hitting this firewall would be instantly incinerated, and its information would be converted into radiation long before it could cross the horizon. This solves the information problem by destroying the traveler before it can create a paradox, but it does so by violating the core principle of general relativity that an astronaut falling into a black hole should notice nothing special as they cross the horizon. For light that is merely trapped in complex gravitational labyrinths outside of any event horizon, the fate of its information is different, though no less strange. A photon caught in a chaotic orbit around a binary black hole system, for instance, is not permanently lost. Its information is still, in principle, accessible. It could eventually escape through the exceedingly slow process of quantum tunneling, a probabilistic trick where a particle can bypass a barrier even if it does not have the classical energy to overcome it. But the timescales for such an escape could be longer than the current age of the universe, making the information effectively, though not fundamentally, lost. This intense conflict at the intersection of gravity and quantum theory is not just philosophical. It forces us to ask what reality is truly made of and whether information is the most fundamental currency of the cosmos. The quest to resolve this paradox is driving the search for a deeper theory of quantum gravity, and it suggests that if we could ever learn to read the subtle imprints of curvature on light, we might unlock technologies that seem like magic today. This mastery of cosmic curvature has evolved into one of astronomy's most powerful tools. We no longer see gravitational lensing as a mere distortion to be corrected, but as a natural telescope gifted to us by the universe itself. By peering through these massive lenses, astronomers can observe galaxies so distant and faint they would otherwise be completely invisible to our most powerful instruments. A foreground galaxy cluster with its immense gravitational field acts as a vast natural magnifying glass, amplifying the light from objects lying far behind it. This technique has allowed us to glimpse the first generation of galaxies, their light stretched and amplified after a journey of over 13 billion years. But the ultimate application of this principle lies even closer to home within our own solar system. A visionary concept proposes using the Sun itself as a gravitational lens. The calculations are precise. At a distance of approximately 550 astronomical units from the Sun, far beyond the orbit of Pluto, there exists a gravitational focus point. Here, the Sun's gravity would bend the light from a distant object directly behind it, creating a perfect natural lens. A telescope positioned at this spot could, in theory, achieve magnifications powerful enough to map the surface of an exoplanet in a neighboring star system, revealing continents and oceans on a world light years away. This is not just an improvement in observation, it is a fundamental leap, turning our star into the primary lens of the most powerful telescope ever conceived. The implications of spacetime curvature are not confined to the edges of the solar system. They are woven into the technology we use every day. The Global Positioning System, or GPS, relies on a network of satellites carrying incredibly precise atomic clocks. For the system to provide accurate location data to your phone or car, it must account for the subtle warping of time itself. According to general relativity, a clock in a weaker gravitational field, like that of a satellite in high orbit, ticks faster than a clock on Earth's surface. Furthermore, the satellite's high speeds introduce a separate time dilation effect from special relativity. If these minuscule relativistic corrections were not programmed into the system, GPS coordinates would drift by several miles within a single day. Your navigation app works because at its core, it is continuously solving Einstein's field equations in real time. This is the most ubiquitous and practical proof that the curvature of spacetime is not an abstract theory, but a physical reality that must be engineered around. As our computational models grow more sophisticated, we are transitioning from passively observing these cosmic labyrinths to actively exploiting them. We are learning to read the intricate patterns of distorted light not just as noise, but as a high-fidelity signal, a detailed map of the invisible mass that caused the distortion in the first place. This allows us to chart the distribution of dark matter with exquisite precision, turning the universe's gravitational funnels into tools for uncovering its deepest secrets. But to truly grasp the nature of this curved reality, we must shift our perspective. How would the universe appear to an observer living deep within one of these gravitational labyrinths? From deep within the labyrinth, the universe would rewrite itself before your eyes. An observer orbiting just outside a black hole's event horizon would witness a sky unlike any seen from Earth. The profound curvature of spacetime would act as a monstrous lens, warping the incoming light from every star and galaxy. Instead of a familiar, star-dusted void, the entire cosmos would be compressed into a single, brilliant band of light encircling the abyss. This luminous ring, an infinitely distorted map of the entire universe, would hover around the black hole's central shadow, while the regions above and below you would plunge into an absolute starless darkness. You would see the same background star not once, but multiple times, its light fractured and duplicated as it navigates different paths through the gravitational maze. The spatial distortion is only half the story. Time itself would become a fluid and unreliable dimension. Due to gravitational time dilation, your clock would tick infinitely slower compared to the clocks of a distant observer. Watching the universe outside, you would see the external cosmos speed up in a frantic blur. Galaxies would spin and collide in fast forward, their stellar lives flashing by in moments. A supernova might erupt and fade in the blink of an eye. Meanwhile, any signal sent to you from the outside would be blue-shifted into a torrent of high-energy radiation, the light of distant stars squeezed into a lethal bath of gamma rays. To a safe observer watching you from afar, your own movements would appear to slow to a frozen halt as you approached the event horizon, your image reddening and dimming until you vanished entirely. These are not just abstract ideas. The visualizations for the film Interstellar, developed with physicist Kip Thorne, gave us a scientifically grounded glimpse of this bewildering perspective. They showed the accretion disk as a thin, fiery halo wrapped around the shadow, bent by the incredible gravity into a complete ring of light above, below, and behind the black hole. This painstaking simulation reveals a fundamental truth. Our experience of reality is not absolute. It is entirely relative to the local geometry of the spacetime we inhabit. The straight lines and steady time we take for granted are simply the product of our position in a relatively flat and calm gravitational field. Step into a cosmic labyrinth, and the very rules of perception are transformed. This dependence on location raises a compelling question. How does the intensity of this curvature vary from one cosmic object to another, and what different kinds of labyrinths do they create? The strength of spacetime's curvature varies as dramatically as the objects that create it. Our own planet Earth generates a gravitational field so gentle that its curvature is almost imperceptible. Yet this slight warp is crucial, bending starlight by a minuscule fraction of a degree and forcing engineers to account for it in the atomic clocks of the global positioning system. Without these corrections, your phone's map would be useless within hours. A step up in scale, our sun creates a more pronounced indent in the cosmic fabric. During a total solar eclipse in 1919, astronomers measured starlight grazing the sun's edge and found it deflected by exactly 1.75 arcseconds. That is a tiny angle, less than 1,000th of a degree, but its precise match to Einstein's predictions shattered the Newtonian view of gravity and confirmed that space itself could be bent. Now compress a star more massive than our sun into a city-sized sphere of pure neutrons. The resulting neutron star possesses a gravitational field so intense that it bends light not by arcseconds, but by entire degrees. Imagine the night sky from the surface of such an object. If you could survive the crushing gravity, background stars would be shifted dramatically from their true positions, some even appearing to hover directly overhead when they are actually far below the horizon. In extreme cases, the curvature can be so strong that a single star behind the neutron star might be lensed into two or more distinct images, a faint celestial mirage dancing around this ultra-dense remnant. But the ultimate expression of curvature lies within the black hole. Here, the gentle slopes of planetary gravity and the steep funnels of neutron stars give way to a vertical cliff in spacetime. The event horizon is not a physical barrier but a mathematical threshold where the curvature becomes infinite. All possible paths for light, every geodesic leading forward in time, curve relentlessly inward. There is no longer an outward direction to travel in. This is the end of the spectrum, the point where the cosmic labyrinth becomes a perfect, inescapable prison. From the subtle warp that guides our satellites to the absolute fold that captures light, this hierarchy of curvature reveals a universe where gravity's architectural influence is both universal and infinitely varied. As the universe expands and evolves, how will these fundamental relationships between mass and curvature change over billions of years? These cosmic labyrinths are not frozen in time. They are living architecture, their walls and corridors constantly reshaped by the motion of the masses that create them. Consider the intricate dance of a binary black hole system. As these two colossal objects spiral around one another, they do not simply carve a static gravitational well. Their orbital motion sends powerful ripples through the fabric of spacetime itself, the gravitational waves we can now detect. Each ripple is a tremor in the cosmic landscape, a propagating change in curvature that momentarily tightens some paths for light while opening others. The labyrinth here is a churning sea of gravity, where a route that was open for a photon one moment might pinch shut the next, only to reopen as the black holes complete another fraction of their orbit. This creates a flickering, dynamic maze where light must navigate a funhouse of gravity whose mirrors are in constant motion. This evolution extends to the grandest scales of the cosmos. The vast cosmic web, that filamentary structure of dark matter and galaxies, is itself a work in progress. Over billions of years, dark matter halos merge, and galaxies collide and cannibalize one another. With each merger, the local curvature of spacetime is rewritten. A gentle gravitational dimple between two galaxies deepens into a profound well as they combine, permanently altering the paths that future light will take through that region of space. The large-scale lensing effects we measure today are therefore a record of this ongoing construction, a snapshot of a curvature landscape that has been under development since the Big Bang. Even the relentless expansion of the universe plays a role in this story. As the cosmos stretches, the average distance between massive objects increases, which acts to dilute the strength of their gravitational influence over intergalactic distances. In an empty, ever-expanding universe, this would mean curvature effects gradually fading away, but this is counteracted by the opposing force of structure formation. While space expands, gravity pulls matter together, creating ever more concentrated clusters and superclusters. These dense knots become the sites of the strongest curvature, the most complex labyrinths. So the cosmic story of curvature is a tug of war between the smoothing effect of expansion and the focusing power of gravity's relentless pull. The map of gravitational potentials that light must traverse is never the same from one eon to the next. The mathematical tools we use to describe these effects must therefore account for this fluid, dynamic nature. The precise mathematics behind these cosmic mirages reveals a universe governed by elegant geometry. To chart a photon's journey through curved spacetime, physicists rely on the concept of geodesics. A geodesic is the straightest possible path through a warped landscape, the natural route an object follows when moving freely. For light, which experiences no other forces, these geodesics are its only guide. The task, then, is to solve the geodesic equation for a photon within the specific mathematical description, or metric, of a given gravitational environment. For a simple, non-rotating black hole, this involves the Schwarzschild metric. For the swirling vortex of a spinning black hole, it requires the more complex Kerr metric. Each solution maps out the exact trajectory a light ray will take, predicting whether it will escape, be captured, or enter a temporary orbit. These mathematical principles come to life through sophisticated computer simulations using numerical ray tracing. This process is akin to firing millions of digital photons from a virtual camera into a simulated universe, meticulously tracking each one as it navigates the programmed curvature. The paths are not guessed, they are calculated by solving the geodesic equations at every point. The resulting synthetic images, whether of a black hole's shadow or the distorted arcs of a lensed galaxy, can be directly compared to real telescope observations. This is how the predictions of general relativity are rigorously tested. The simulations have grown incredibly advanced, now integrating general relativistic magnetohydrodynamics. This mouthful simply means the models can also account for how light interacts with the superheated, magnetized plasma swirling in accretion disks, adding another layer of realism to our virtual cosmic laboratories. These tools transform the abstract philosophy of curved space into concrete, testable physics. They allow us to decode the universe's hidden architecture by reading the subtle deflections of starlight. But this mastery of the cosmic labyrinth's mathematics inevitably leads us to a more profound inquiry. If our entire perception of reality is filtered through this curved and twisted medium, what does that reveal about the nature of the cosmos we think we see? Our perception of the cosmos is a carefully constructed illusion, sculpted by the invisible hand of gravity. We gaze at the stars and believe we see their true positions, their authentic forms, but we are always looking through a lens of curved spacetime. This fundamental truth forces a profound philosophical shift. If a single quasar can appear as four distinct points of light, which one is the real object? The astonishing answer is that they all are. Each image is a genuine physical representation of the quasar, its light having traveled a unique geodesic through the cosmic labyrinth. There is no single privileged perspective in a curved universe. Each path is a valid, though incomplete, chapter of the same story, and only by combining them all do we approach a fuller understanding of the source. This multiplicity of realities extends into the dimension of time itself. When we observe a supernova explosion replay in a second lensed image months after the first, we are witnessing a direct challenge to our classical notion of simultaneity. The event happened once at a single moment in its own local time, yet from our distant vantage point, the curved geometry of spacetime presents it to us as two separate occurrences. This means that the very idea of now becomes fluid, dependent on the observer's position within the gravitational landscape and the specific, winding path that light has taken to reach them. Our telescopes do not offer a clear window onto an objective reality. They provide a filtered, interpreted, and often distorted view, a map that has been folded and crumpled by the mass it seeks to represent. To know the universe, we must first learn to read the intricate folds of the map itself. This beautiful, mediated relationship between the observer and the cosmos has not been lost on those who translate wonder into art, inspiring creators to visualize the invisible architecture of gravity. Artistic visions give form to the invisible architecture of the cosmos. The film Interstellar presented a landmark depiction of a black hole, Gargantua, a visualization born from a unique collaboration between director Christopher Nolan and physicist Kip Thorne. To create it, Thorne's team wrote millions of lines of code, solving Einstein's equations to render how light would truly behave around a spinning black hole. The result was not what anyone expected. The accretion disk, that swirling disk of superheated gas, did not simply appear as a flat ring behind the shadow. Instead, the intense gravitational lensing warped it into a brilliant, shimmering halo that wrapped over the top and under the bottom of the central darkness, a perfect illustration of how curved spacetime distorts our entire field of view. This was not artistic license, it was a window into a real physical phenomenon. Beyond cinema, digital artists and programmers have built interactive simulations that let you pilot a virtual camera through these warped landscapes. You can watch as background stars stretch into streaks of light and see how the paths you travel are not straight lines but geodesics, the natural curves carved by gravity. These tools transform abstract mathematics into a visceral, navigable experience. For more accessible demonstrations, science centers often use the classic analogy of a stretched rubber sheet. A heavy ball bearing placed in the center creates a depression, and rolling a smaller marble nearby shows how its path curves inward. This simple model powerfully conveys the core idea that mass tells space how to curve. Yet it is a simplification of a far richer reality. The rubber sheet represents a two-dimensional surface, while real spacetime is a four-dimensional fabric, and gravity is not a force pulling down but the geometry of the surface itself. These creative endeavors, from blockbuster films to classroom models, are more than just illustrations. They are essential translations, converting the dense language of tensor calculus into stories and sensations we can all grasp. They build a bridge of intuition, allowing us to feel the curvature of the universe in our minds. With this foundation of understanding, built through both science and art, we are now poised to test these ideas with unprecedented clarity. A new generation of telescopes is coming online, armed with the power to map the cosmic labyrinth in stunning detail. The next generation of telescopes will soon transform our entire view of the cosmic labyrinth. The Vera C. Rubin Observatory, with its monumental camera, will not simply take pictures of the sky. It will capture a continuous 10-year-long movie of the cosmos. By monitoring billions of galaxies, it will catch the fleeting flickers of distant supernova being magnified by gravitational lenses, and it will map the subtle shearing of galaxy shapes from weak lensing on an unprecedented scale. This colossal survey will uncover tens of thousands of new gravitational lenses, turning rare cosmic mirages into a vast statistical dataset that reveals the dark matter skeleton of the universe in exquisite detail. Simultaneously, the space-based LISA mission will open an entirely new sense, allowing us to hear the curvature of spacetime itself. While telescopes see the static snapshots of these labyrinths, LISA gravitational wave detectors will listen to the dynamic groans and shudders as massive black holes spiral together and merge, feeling the very walls of the labyrinth shift and reconfigure in real time. These advanced interferometers, along with the coming 30-meter class telescopes on the ground, will resolve details in strongly lensed systems that are currently just blurry smudges. We might see the subtle, telltale asymmetries in an Einstein ring that betray the furious spin of the central black hole warping spacetime around it, or detect the faint, secondary images of stars that have traveled around the gravitational well multiple times. This new era is not just for professional astronomers. Citizen science projects like space warps have already proven that the human eye is remarkably adept at spotting the elegant arcs and strange symmetries of gravitational lenses in vast datasets. By engaging the public in this cosmic treasure hunt, these projects tap into our collective curiosity, accelerating the discovery of new and ever stranger labyrinths. As our vision sharpens, we may even discover entirely new classes of cosmic traps. Could the gravity of a boson star, a hypothetical object made of ultralight particles, create a lensing signature unlike anything we have seen? The future promises to reveal curvature phenomena that we cannot yet even imagine. With these powerful new tools on the horizon, what fundamental mysteries about gravity and the cosmos remain stubbornly out of reach? Even with our most powerful tools, the deepest nature of the cosmic labyrinth remains shrouded in mystery. We still do not know the ultimate fate of the information carried by a single photon as it vanishes across an event horizon. Does its story truly disappear forever, or is it somehow preserved, scrambled onto the surface of the black hole like a cosmic hologram? This information paradox is a profound crack in our understanding, a place where general relativity and quantum mechanics offer completely contradictory answers. Another theoretical puzzle is the naked singularity, a point of infinite curvature completely unshielded by an event horizon. Such an object would expose the raw, broken geometry at the heart of gravity for the entire universe to see. Most physicists believe nature abhors such a spectacle, a concept called cosmic censorship, but a definitive proof remains one of the great unsolved problems in theoretical physics. At the very smallest scales, where spacetime is thought to churn in a quantum foam, our current theories fail entirely. We lack a working theory of quantum gravity to describe the labyrinth's foundation, leaving us guessing at the true nature of reality at the Planck scale. Even our observations present new riddles. Astronomers see more of certain strong lensing events, like perfectly formed Einstein rings, than our best models of dark matter predict. This could mean dark matter interacts with itself in ways we have not anticipated, or that our understanding of how curvature behaves in colossal galaxy clusters is still incomplete. The tantalizing possibility of wormholes, those cosmic shortcuts, also endures. While no evidence exists, scientists continue to search for their ghostly imprints, perhaps in the subtle patterns of the cosmic microwave background, or hidden within the complex chirps of gravitational waves. These are not dead ends, but the very frontiers of discovery. To navigate them, we must first learn to see the universe through the lens of curvature itself, a perspective that begins not in advanced laboratories, but in our most fundamental educational journeys. Mastering these cosmic concepts begins with a simple, stretched fabric. In classrooms worldwide, a spandex sheet and a heavy ball become a universe in miniature. The ball's weight creates a depression, and a marble rolled nearby traces a curved path, a visceral demonstration of how mass warps space. This classic model provides that crucial first intuition, but it is only the beginning. To move beyond a two-dimensional analogy, educators now employ virtual reality, creating immersive simulations where students can fly around a virtual black hole, watching from all angles as background starlight stretches into arcs and rings. They are not just learning about curvature, they are experiencing a navigable labyrinth. The educational journey is carefully scaffolded. It starts with those physical analogies, progresses to interactive computer simulations that map photon trajectories, and only at the most advanced levels introduces the full power of Einstein's field equations. The goal is to build understanding layer by layer, ensuring the mathematics describes a reality the student can already feel in their mind. Planetariums have become powerful partners in this effort. Their domed screens are perfect for projecting scientifically accurate visualizations of gravitational lensing, placing an audience directly inside a galaxy cluster to watch the light from distant quasars split into multiple shimmering mirages. Science museums feature exhibits where you can manipulate a laser's path across a curved surface, seeing firsthand how the straightest line is not always what it seems. For the self-directed learner, online tools offer interactive geodesic calculators. With a click and drag, you can adjust the mass of a simulated star and instantly see how the possible paths for light tighten from gentle curves to closed loops. This direct engagement transforms an abstract concept into a dynamic, personal discovery. These multifaceted approaches are essential. They ensure the profound idea that our universe is a geometric fabric filled with invisible, twisting labyrinths is not reserved for a handful of theorists but becomes a fundamental part of our shared cosmic literacy. This collective understanding invites a final, reflective question about our place within this curved reality. These cosmic labyrinths are far more than just celestial curiosities. Their existence fundamentally shapes how we interpret every single piece of light that reaches our telescopes. When we measure the distance to a faraway supernova or calculate the age of the universe, we are relying on data that has been subtly, and sometimes dramatically, altered by its journey through curved spacetime. To get the right answers, we must first learn to read the distortions of the labyrinth. This precise mapping of gravitational lensing has become an indispensable tool for cosmology. By analyzing how light bends, we can measure cosmic distances with incredible accuracy, which in turn refines our understanding of the universe's expansion history and its ultimate fate. Every corrected mirage brings us closer to knowing whether the cosmos will expand forever or eventually collapse back on itself. These extreme environments also serve as the ultimate natural laboratories. We cannot create a black hole on Earth to test Einstein's ideas, but the universe provides them for us. By observing how light behaves at the very edge of an event horizon, or how spacetime ripples when two black holes collide, we are stress-testing general relativity under conditions of unimaginable gravity. Each observation is a crucial experiment, probing for any tiny crack in the theory, any slight deviation that might point toward a deeper truth. This is how science progresses, by pushing established ideas to their absolute limits. Beyond the equations and the data, these phenomena force a profound philosophical shift. The realization that a single object can have multiple, equally real appearances, or that the flow of time is not universal but depends on your place in the gravitational landscape, challenges our most basic assumptions about reality. Our perception is not a clear window onto the cosmos. It is a filtered, interpreted view, mediated entirely by the physical laws of a curved universe. To know the cosmos, we must first understand the lens through which we are viewing it. Ultimately, this entire journey through the twisting paths of lost light represents something deeply human. It is our enduring quest to map the hidden architecture of existence, to understand the fundamental rules that sculpt everything from the orbit of a planet to the fate of a galaxy. We are piecing together the blueprint of the cosmos, one bent photon at a time. This grand puzzle reminds us that the universe is not just a collection of objects, but a dynamic, geometric fabric, and we are privileged to be within it, slowly learning to trace its intricate and beautiful folds. Our journey through the cosmic labyrinths ends not with a final answer, but with a new way of seeing. We have traced the paths of lost light, from the gentle curve that displaces a star's image to the absolute fold of an event horizon where paths forever close. This invisible architecture of curved spacetime is not a flaw in the cosmos, but a fundamental feature, a universe built not on rigid lines but on fluid, dynamic geometry. The challenges this curvature presents are profound, forcing us to decode mirages and account for the subtle shearing of every distant galaxy. Yet these same challenges gift us with unparalleled opportunities, turning massive clusters into natural telescopes and allowing us to map the unseen dark matter that sculpts the cosmic web. These phenomena whisper a consistent truth that the universe operates on principles of elegant geometry, principles that often defy the intuition forged in our relatively flat and calm corner of space. Grasping them requires the twin engines of rigorous mathematics and boundless creativity. As our tools evolve, from the Vera C. Rubin Observatory's relentless gaze to the space-based ears of Lisa listening to gravitational waves, our maps of these labyrinths will deepen in resolution and complexity. Each new detail will solve one mystery only to reveal another, an endless frontier where theoretical insight and observational brilliance converge. So the next time you look up at the night sky, remember that you are not looking at a simple void. You are gazing into a vast, dynamic labyrinth, a cosmos filtered through the invisible lens of gravity itself. What wonders do you think are still hidden within its folds? Share your thoughts and questions in the comments below. The story of how we learn to see these cosmic labyrinths is a journey of its own. For centuries, Isaac Newton's view of gravity prevailed, a universe governed by an invisible force pulling objects together. He even speculated that light, which he thought was made of tiny particles, could be pulled by gravity, its path bending ever so slightly as it passed a massive star. This was the first hint, a whisper of the truth. Early astronomers tried to catch this bending during solar eclipses in the 19th century, but their searches came up empty. They were looking for a deflection based on Newton's math, a tiny angle that was simply too small to be seen. The universe was hiding a much deeper secret. Then came Albert Einstein. In 1915, he presented a theory that reimagined reality itself. Gravity was not a force, he said, but a consequence of geometry. Mass and energy curve the very fabric of spacetime, and light simply follows those curves. His equations predicted a bending angle exactly twice what Newton's theory suggested. The stage was set for a dramatic test. In 1919, during a total solar eclipse, two expeditions led by Arthur Eddington traveled to opposite sides of the globe to measure the positions of stars appearing near the darkened sun. The results were unmistakable. The starlight was deflected by precisely the amount Einstein had calculated. A new cosmic picture snapped into focus. Suddenly, the bending of light was not a speculative idea but an observable fact. Einstein became an international celebrity overnight, and general relativity was catapulted from abstract theory to a cornerstone of modern physics. This historical pivot shows us that scientific progress is not a straight line. It is a process of building on the insights of the past, like Newton's, while having the courage to overturn fundamental misconceptions. Our ability to map today's cosmic labyrinths rests entirely on that pivotal moment when theoretical brilliance was confirmed by the patient gathering of starlight during a few precious minutes of totality. The same cosmic curvature that baffles physicists has also captured the creative spirit of our time. Arthur C. Clarke's visionary novel, The Light of Other Days, presents a world transformed by a device that uses microscopic wormholes to bend light, effectively allowing people to see any point in space or time. This is not magic, but a fictional extension of gravitational lensing pushed to its ultimate extreme, turning the entire planet into a transparent labyrinth where privacy vanishes and history becomes an open book. Similarly, the film Contact, based on Carl Sagan's work, grounds its interstellar journey in a plausible, if speculative, use of a wormhole, a tunnel of profoundly curved spacetime that lets a lone traveler bypass the void between stars. These stories resonate because they take the cold mathematics of relativity and weave it into deeply human narratives of discovery and connection. The interactive realm of video games has taken this a step further, offering not just stories but experiences. In the Universe Simulator Space Engine, players can pilot a virtual ship directly into the vicinity of a black hole, watching in real time as the background cosmos warps into a perfect, shimmering Einstein ring. The controls in your hands are not just moving a character, they are solving the geodesic equation in real time, allowing you to feel the gravitational whirlpool tug at your path. This is public education at its most powerful, transforming players from passive observers into active navigators of the cosmic maze. While these depictions sometimes take creative liberties for the sake of drama, their greatest success lies in translation. They have taken concepts that once lived only in dense academic journals and rendered them into the language of wonder, making ideas like spacetime curvature accessible and thrilling to millions. The global excitement surrounding the first direct image of a black hole, a fuzzy orange ring that instantly became a cultural icon, proved how deeply these ideas can resonate. That public captivation is not a trivial side effect. It is the very fuel that sustains ambitious, fundamental research. When a society is collectively amazed by the shadow of a black hole or the concept of a wormhole, it creates a powerful mandate to keep building bigger telescopes and funding the complex theories that try to explain it all. This cultural dialogue between science and art ensures that our exploration of the cosmic labyrinth remains a shared human endeavor. The language of cosmic curvature finds its purest form in the abstract beauty of differential geometry. This branch of mathematics provides the vocabulary and grammar to describe how any surface, from a simple sheet of paper to the four-dimensional fabric of spacetime, can bend and twist. Without this mathematical foundation, concepts like the geodesic path of a photon would remain vague philosophical notions, impossible to calculate or test. But equations alone are not enough to visualize a black hole's shadow. This is where computer science enters the labyrinth, employing sophisticated numerical algorithms to solve Einstein's field equations across billions of digital points. These simulations, running on some of the world's most powerful supercomputers, trace the paths of countless virtual photons, allowing us to watch a cosmic mirage form in a virtual universe before we ever point a telescope at the real thing. This computational power transforms raw theory into a testable visual prediction. Remarkably, we can also create miniature versions of these cosmic effects right here on Earth. Materials scientists engineer structures known as photonic crystals, where light propagates through a carefully designed lattice as if it were moving through a powerfully curved space. By studying how light bends and twists within these laboratory-scale models, we gain practical insights into the behavior of light navigating the gravitational wells of distant stars and galaxies, bringing the cosmos into the lab. Our ability to comprehend these phenomena, however, is filtered through the lens of our own perception. Cognitive scientists investigate how the human brain struggles to intuitively grasp non-Euclidean geometries. We are evolutionarily wired for a flat, local world, making the concept of a closed universe or a spatial loop incredibly difficult to visualize. Our mental models often fail us, revealing both the incredible adaptability of human thought and its inherent limitations when confronting the true, warped nature of reality. This interplay between mind and curved space even inspires creative fields. Architects and urban designers draw upon concepts of perceptual curvature, creating structures with undulating walls and clever mirrors that warp a visitor's sense of space and perspective, much like gravitational lensing warps our view of the cosmos. These interdisciplinary threads, from the pure logic of mathematics to the artistry of design, all weave together. They show that the principle of curvature is a universal idea, a pattern that resonates across the sciences and the arts, deepening our appreciation for the structured, yet beautifully warped, nature of existence itself. You can step directly into a simulated universe and feel the pull of a black hole for yourself. Free software like the Einstein Toolkit offers a powerful gateway, providing open-source frameworks for numerical relativity simulations that run on a home computer. With this tool, you are not just watching a video, you are setting the initial conditions for virtual stars and watching how their immense gravity sculpts the spacetime around them in real time, according to Einstein's own equations. For a more visual and immediate experience, many popular planetarium programs now include dedicated gravitational lensing modes. With a few clicks, you can place a virtual black hole in front of a field of stars and watch as it twists the entire celestial background into a perfect, shimmering Einstein ring, bringing the cosmic mirage to life on your screen. These digital tools reveal the mathematics in action, but the core concept of curvature is powerfully simple. A classic classroom demonstration uses a stretched lycra sheet and a collection of marbles. Placing a heavy ball bearing in the center creates a deep, smooth depression. When you roll a smaller marble nearby, its path naturally curves inward, faithfully tracing the contours of the warped fabric. This is not just an analogy, it is a direct physical model of how mass tells space how to curve, and how that curved space then guides the motion of everything within it. To bridge the gap between a physical model and precise calculation, online geodesic calculators are incredibly effective. You can input different masses from a star to a black hole and instantly see a map of how light paths would bend around them. Watching those trajectories tighten from gentle arcs to closed loops as the mass increases gives you an intuitive feel for how a cosmic labyrinth is drawn. For those who enjoy coding, writing a basic ray tracing algorithm to visualize light paths in curved space is a deeply rewarding challenge. You program a virtual camera to fire photons into a digital gravitational field and then meticulously calculate their deflected paths. This hands-on process demystifies the underlying mathematics, transforming abstract tensor calculus into a tangible, visual output you created. These practical exercises, from simple fabric models to complex simulations, make the invisible architecture of the universe something you can not only understand, but actively explore and manipulate.